So this talk is called Generic Rigidity and the Grassmannian. So if you put a graph into the plane, giving its vertices coordinates, the Geringer-Leman theorem says that to see if it's rigid or flexible, you just look at subgraphs, count how many edges they have, and as long as the number of edges is less than or equal to 2v minus 3, twice the number of vertices minus 3, then you're good. If all subgraphs are sparse like that, edge sparse, not too many edges, then the graph is rigid. This kind of edge sparsity count on subgraphs fails in 3 dimensions and higher. Simplest example is, so the octahedron on the left satisfies all the sparsity conditions, and it is rigid, as you'd expect. But this double banana graph on the right satisfies all the sparsity conditions on subgraphs, and yet it is flexible. So given what's going on in more detail, given a placement of the vertices into some Euclidean space, we can get other placements x. So given the placement p, we can get other placements x with the same edge lengths just by rotating and translating all the points uniformly in that Euclidean space. So we get a bunch of other placements once we have one. And if that's it, if those are the only ways to get other placements with the same edge lengths, we say that the placement P is locally rigid. But if there are more ways to get placements with the same edge lengths that aren't just rotating or translating, then we say it's locally flexible. So a placement is locally flexible basically if the dimension of some algebraic variety is, actually this should be strictly greater than, it's locally flexible if the dimension is strictly greater than Euclidean motions, meaning there's more ways to satisfy the edge length conditions than there are translations and rotations. So the edge length equations are just like this. It just says that the new placement x should have the length of edge 1, 2 minus the length of the edge 1, 2 in the placement p be 0. So they have the same edge length. And if you just require that for all the edges, then you get some algebraic variety inside of r to the n, or vd, where v is the number of vertices, d is the dimension. So at a generic placement, we can see the dimension from the right kernel of the Jacobian, and it's pretty intuitive. Imagine a curve of placements passing through the given placement P. Then visualize the velocity of that curve of placements by splitting it vertex by vertex. So for example, here's in a picture with 4 vertices. You can imagine a vector in the right kernel of the Jacobian as splitting it into each vertex separately, and you just put these 4 red vectors. 2 of them are 0 vector. And to first order, the Jacobian of an edge length equation is going to be like, for example, here at vertex 1, this red arrow is orthogonal to edge 1, 4. So it's going to preserve the edge length to first order of edge 1, 4. So it's good on this second row. This multiplication will be 0 on the second row because it's 90 degrees. For edge 1, 2, this v1 is going to multiply and dot product with the edge vector e1, 2 and give a non-zero number. But because the other red one is exactly going to cancel it, then it's also good on edge 1, 2. So if it's good on all the edges, first order accurate, we get this sort of picture of infinitesimal flexing of this framework. So that's actually pretty intuitive, the right kernel of the Jacobian matrix. And let's just look at the Jacobian in a little bit more detail. Remember, here's the edge length, edge 1, 2 equation. If we take the partials, what you see is the 2 comes down, and there's a minus sign. And if we just sort of ignore that, we see that these first 2 coordinates are really the edge vector e1, 2. I think technically they're negative e1, 2 divided by 2 or multiplied by 2, but let's just ignore that. Rescaling it won't change the rank at all, and that's what we care about. And if you look at the second 2 coordinates, you're just going to get minus e1, 2. And then all of the rest are 0 on this edge vector 1, 2 because the edge length of 1, 2 only corresponds to the variables vertex 1 and vertex 2. So that's why we have all zeros in the rest of this top row. So the right kernel is intuitive. Its dimension tells us rigid and flexible. But I want to look at the left kernel instead. Which elements of the left kernel are going to be called self-stresses. Elements of the right kernel were called infinitesimal flexes. So what's a self-stress? Well, it's actually pretty intuitive as well. If you built one of these things and you wanted to know if it's rigid, you just start pressing on it, trying to push vertices together at a missing edge. And if the framework resists your push, it is resisting through its edges. Some stresses and strains on the edge are perfectly, these three edges here are going to push back on this vertex to perfectly balance and go the opposite way of what you're pushing. So this sort of looks like we have these weights, which represent the stress or strain. And for example, let's look at vertex 4. It's kind of interesting. If you pushed on it here, it has to counterbalance you on vertex 1. But what about at vertex 4? Now we have these 4 edges that are under stress, and they're going to exert forces at vertex 4. And we call it balanced at vertex 4 if those forces all cancel to 0. Right? And that's actually what you would want. If they don't cancel to 0, then vertex 4 is going to start moving. And so if this thing can resist your push, what we get is W times the rigidity matrix equals the push vector, the force vector that you are applying, which of course has zeros everywhere where you are not pushing. Okay, so this is the intuition of sort of how you would actually tell rigidity from something involving stresses on the edges. But we can turn that into a self-stress where WA equals 0, not the force vector, by just sort of adding this edge. Like if we just add this edge in, then instead of me pushing on it, we can think of a stress on that edge. And so this F15 becomes E15. This minus F15 becomes minus E15. It just becomes another row. And the exact, we're just moving a term to the other side of the equation, and we get a self-stress. So really pushing on the thing and self-stresses are basically the same, just that whether you're viewing an edge in the graph or whether you're viewing it as being removed. And they also tell you rigid and flexible, because if we look at this picture cartoon of the Jacobian, we're wondering if the kernel always has D+1 choose 2 translations and rotations, which I'm visualizing sort of as columns after Gaussian elimination. These columns correspond to free variables. And we want to know if there's one more. Well, if there's something in the left kernel and we have exactly the right number of edges, then something in the left kernel means there's also something more in the right kernel. So it's basically that you can tell the rank of a matrix by looking at its left kernel or by looking at its right kernel. So that should make sense. It also sort of gives us a new perspective on the double banana being flexible. The most intuitive perspective on why this is flexible is you look at this sort of axis here and you imagine rotating one banana around that axis, but keeping the other fixed. That is not a rotation of all of space, and so it is a flex. Because you're fixing one banana and rotating the other, you're not rotating all of space. So this is a flex. And this is the most intuitive way to see that this is a flexible graph. But there's a different, maybe a slightly less intuitive way, is that this banana here is capable of resisting this force, but this banana is capable of resisting this force. So if you put them together, they can cancel out and give you a self-stress. That self-stress drops the rank, which then opens up an infinitesimal flex here. Okay, so to understand when a self-stress exists is to understand rigidity and flexibility by this cartoon rank of a matrix. Big picture of what we're going to do. Number 1, we're going to build a directed acyclic graph on the edges of our original graph, with weights being the signed volumes of certain simplexes, or just choices of D+1 vertices. We're going to sum the product of the weights flowing from some source edges, which I'll explain, to some sink edges, which I'll explain. And the Plücker relations on the Grassmannian, meaning relations on signed simplex volumes, will say if those flows balance, and if those flows balance, we get a non-zero self-stress. Okay, so that's one way to look at it. Now, a different way to say the same thing is you're going to, number one is build a bunch of tableaux, which are combinatorial objects. They're going to be boxes filled with vertex labels like vertex 1, vertex 2, vertex 3. We're just going to label these boxes. And basically number 1 and 2 over here are equal to number 1 here. Then we're going to apply the tableau exchange rules, which are sometimes called Young's straightening rules. And that's the Plucker relation, so that's number 3. And then number 3 here is, I don't know, it just determines rigidity. So build tableau with vertex labels, apply exchange rules. We'll know whether it's rigid or flexible. These are two ways to say the same big picture. I couldn't decide which was a better way to explain it. But let's go into the details. So here are just a kind of a cartoon of the signed volumes. So I'm going to claim that if you press on this edge here, this missing edge, then the weight in edge 1, 3, this weight right here, will be equal to a ratio of this volume divided by this volume. And the weight on 2, 3, which is this one, will be a ratio of this volume divided by this volume. And that's not obvious, but let's look at why. So we'll look at why with a different example. This is now going to be a self-stress. We're going to look for a self-stress. And we'll look at the edge 4, 5 down here. And I claim that it's equal to this ratio of simplex volumes, or tetrahedron volumes in this case, times the weight on edge 0, 4. So that's what I want to explain. So first, if we just look at vertex 4, we're going to have a self-stress means that all the forces from these 4 edges need to balance to 0. That's a self-stress at vertex 4. And so we're just going to move the 0, 4 term to the right side. We'll bring it up here. Cramer's rule says that we can look at this equation. This is a number times a vector plus a number times a vector plus a number times a vector. And we can solve for this number W4, 5 by a ratio of determinants. Okay, we're plugging in the right-hand side for this third column on the top and then dividing by the determinant of the 3 by 3 column in the bottom. Okay, but E41 is P1 minus P4. It's the edge vector between vertex going from 4 to 1, so it's 1 minus 4. And we do the rest of these replacements. We can also, by multilinearity, pull out this scalar. And then I'm going to expand it, add an extra column and an extra row, where I'm just adding P4 and a 1. It doesn't change the determinants at all. Why would I do that? Well, because now I can add this column to the previous columns and just make it the determinant of this 4 by 4 matrix, whose columns are vertex 1, 3, 0, and 4, which I'm going to denote 1, 3, 0, 4. So this 1, 3, 0, 4 really means this determinant. And it's a signed volume of the simplex on vertices 1, 3, 0, 4. Good, so that proves the claim. Great, so now we can find the weight on edge AB by just writing out the balancing condition, the self-stress condition at vertex A. So I'm picking vertex A and I'm saying if all these forces balance at A, which they have to if we have a self-stress, they have to balance at A. They have to balance everywhere, but let's just look at A. Then I'm going to move all these AC terms to the right side and solve for WAB by exactly what I did last time. This time I have a sum in the last column. Multilinearity, I can pull out that sum with the weights, and I have these signed volumes. I have this minus sign here from moving the term to the other side, which is annoying, so I'll just flip 2 of the columns in one of these determinants, which then absorbs the minus sign. And so here's my formula. Now later I'm going to call this ratio of volumes a weight on a directed acyclic graph whose nodes are the edges. So edge AB to edge ACI will be an arrow in this graph on the line graph of the original graph, and it'll have this weight. Okay, but we'll do that later. Okay, good. So now we can find all the WABs by just doing Cramer's rule at vertex A. Awesome. One problem. the octahedron has no self-stress. Okay, so I was looking at for weight 4, 5 or whatever, weight AB, and I find a formula for it, but the octahedron has no self-stress. So really, the question is, when do these local solutions glue together into a globally non-zero solution? So what I did is I just looked at vertex A, and looked at the balancing conditions there, and I can solve. Okay, but we need it to balance not just at vertex 4, but at all the vertices. So when do they glue together? That's the question. Here's another example just to show you how why they don't just automatically glue together. So let's look at edge 6, 8. Then it's a ratio of these volumes here, okay, in which expresses it in terms of edge 5, 8. So 6, 8 can be expressed in terms of 5, 8. Okay, you can kind of view it as going from the red and then swiveling over to the blue. Requires these two volumes. But we could also relate 6, 8 to 4, 8, or maybe 6, 8 to 7, 8, or maybe 6, 8 to 4, 6, or 6, 8 to 6, 7, or 6, 8 to 5, 6. And all of these are completely valid, accurate representations with completely different ratios of volumes. And that's just vertex 8 and edge 6, 8. So we really have to organize the dependencies among these various edge weights. So how will we do that? At each vertex, choose D incoming edges and use Cramer's rule to view each of those D incoming edge weights as determined by all the other edges at that vertex. Okay. So an example, two examples, in D equals in dimension 2, we choose these two edges to be determined by 1, 2. Okay. And over here in dimension 3, we have to choose 3 edges to be determined by 5, 8. Okay. So for very concretely, edge 1, 3 and 1, 5 are determined in terms of 1, 2 by these signed ratios. Over here, we've got edge 6, 8, 4, 8, and 7, 8 are all determined in terms of the outgoing edge 5, 8. Okay, and we're now going to view these as determined. So what we're going to do is choose D incoming at every vertex now. So I've done it there and I've done it there. And all I've done is just completely arbitrarily chosen D edges as incoming at every vertex. Okay. So every edge now has either 0 arrows, 1 arrow, or 2 arrows. We're going to call them sink, stream, source. So over here, edge 1, 2 is a sink. It has no arrows. It's not been determined by either of its endpoints. Whereas edge 1, 3 has 2 arrows. So it's actually determined at vertex 1 and it's determined at vertex 3. That might be a problem. Whereas edge 1, 5 is purely and uniquely determined by vertex 1. And so it's uniquely determined. We're only going to use edges where there's at least D plus 1 because a self-stress is always supported on such edges. You can't linearly combine D generic vectors and get a non-trivial dependence. Also, if you just look at the streams, they make a digraph, a directed graph. If there's any oriented cycles in that stream digraph, you can always remove them by flipping one stream to a sink and the other to a source. And now you don't have an oriented cycle anymore. So assume we've done that as well. So sinks then are free. Streams are uniquely determined by the sinks. Because there's no cycles anymore, that would loop back around and determine a stream in terms of itself, which would be bad. But now we can get rid of them. And so sinks are free. Streams are uniquely determined by sinks. But sources are determined in 2 ways in terms of the sinks. Setting them equal gives a linear homogeneous equation in the sink variables. Okay, so edge 1, 3 is determined by weight 1, 2 in one way from vertex 1 and in a separate way from vertex 3. So just to look at edge 1, 3 right here, we've got very concretely that 1, 3 is this ratio times 1, 2. But from the other vertex 3 endpoint, we go from edge 1, 3 over to 2, 3. Then we go from 2, 3 over to 1, 2. And we now have this separate way. So really, if we set these equal and move everything to one side, we see that we get a linear equation in W12. That's the first equation is just this first row from source 1, 3. And then we've also got source 3, 6, 4, 5, and 4, 6. So we've got 4 equations. So a self-stress needs the weighted paths in the line graph from the source to a sink to balance out. So again, let's look at 4, 6. We go from 4, 6 at vertex 4, we go over to 2, 4, which then goes over to 1, 2. So that's actually this 2-factor term. And if we go from the 4, 6, but from the other vertex, we go swivel over to 5, 6, swivel over to 1, 5, swivel over to 1, 2. That gives us this. So we're just looking along weighted paths in this line graph from the source to the sink, and they should balance out. If they balance, we have a self-stress in our graph. With 2 sinks, you need to check the balance with 2 sources. Okay? The Lindstrom-Gassel-Vianot lemma, I mean, it says a couple different things. It says the maximal minors being 0. So let's say this equation, the maximal minors being 0, is still asking actually for weighted paths from sources to sinks to balance out. So it's really the same. It's going to be the same thing. It actually says more. In particular, the LGV lemma says that you don't need to compute all of these different paths. You only need to compute the edge disjoint, their node disjoint paths. For us, our nodes are the edges. And so the edge disjoint paths. So for example, all of these sources up here, we've got 1, 2, 3 sinks. And so you'd have to look at paths from 3 sources to those sinks. But if you choose any 3 sources up here, the paths to these 3 sinks are going to be forced to go through these 2 edges. And so at least 2 of them will overlap. And so LGV says immediately that's 0. So we don't even have to check these sources up here because there's sort of a bottleneck here that forces them to cross. And LGV lemma says, nope, that just zeroes out. The corresponding determinants or minors are just automatically 0, which is pretty nice. So just a more concrete example, I did that same graph, but I added an extra edge. So now it will admit a self-stress. In other words, this will have a non-zero solution. And what are the entries here? Well, this entry is just corresponding to the paths from 1, 3 to 1, 2. So if we go from 1, 3, how do we get to 1, 2? Well, we can go this way and then rotate this way, or we can rotate this way. And that goes here. And LGV lemma says that you can really just look at this as a sum over disjoint path systems and just product of the weights, where the weights are these ratios on these. I'm sort of viewing them as almost like swiveling from one edge to another. Okay. So so I won't go into more details unless people ask questions, but summary. Build the source stream sink thing on the graph, okay? Then number 2, follow the weighted paths in the line graph, so swiveling from the sources to sinks. Number 3, the Plücker relations tell you if they balance, which means a self-stress will exist. So this is number 3. I need to explain this. So to check for a self-stress, we need to check things like whether this is 0, right? That was that 4 by 1. In other words, weight 1, 3 had 2 ways to get there, and they have to balance. Okay. So when is this 0? Well, we clear denominators. By genericity, all these minors are non-zero, so we can clear them without doing anything bad. Now here's the next step. We're going to rewrite this. So 5, 1, 2, I'm going to rewrite so it's strictly increasing 1, 2, 5. And I'm going to write it as a column now. Instead of the 5, 1, 2, I'm going to write the column 1, 2, 5. Instead of 6, 1, 3, I'm going to write 1, 3, 6. And 4, 3, 2 becomes 2, 3, 4. Okay. And I have to adjust by signs to do this. So for example, to rewrite 4, 3, 2 as 2, 3, 4, I need to push the 2 to the front. That's 2 swaps. And then I need to switch the 3 and 4. That's a third swap. So there's technically a minus sign that needs to be added or multiplied by to go from 4, 3, 2 to 2, 3, 4. But then some other minus sign here cancels out and we get a plus. This minus becomes a plus because of the swapping that's required. And so this is just how I'm going to write it. These are called tableaux, and they are strictly increasing down each column. And then I'm going to also, I can swap the columns now because you can multiply these determinants in any order. And so I can rearrange the columns to be in lexicographic order, which means sort of 1, 1, 2, 2, 3, 3, 4, 5, 6. Well, no. Lexicographic order means 1, 2, 4 is less than 1, 3, 5 because they agree on 1, but 2 is less than 3. So that's why I put 1, 2, 4 on the left and 1, 3, 5 on the right. Okay, so you can always do that. You can always strictly increase, and you can always put them in lex order. Now, expressions like this that are sort of secretly true are the reason that graphs are flexible. So in other words, the graph plus the Plucker relations tells you rigidity and flexibility. Because you look at this, and you're wondering, is this secretly zero? At first, it looks like, no, these are completely different expressions. But these are volumes of tetrahedra, in other words, Plucker coordinates on the Grassmannian, and they can sometimes be secretly zero because of interesting Plucker relations. Okay, so when these are secretly equal, then we get flexibility. So again, we have this edge 1, 3, 2 ways, gives you this, gives you this. Now here, how are we going to decide whether this is secretly equal or not? Well, thankfully, there's a well-established combinatorial algorithm called Young's straightening law that solves this problem. Okay, and there's different versions of it. This one, we're going to call it standard because it's weakly increasing along the rows. This one, although it's in lex order, 1, 2, 5 is less than 1, 3, 6. 1, 3, 6 is less than 2, 3, 4 in lex order. It's not standard because 5, 6, 4 has a violation, the 6 and the 4. The 6 is bigger than 4, so that's not good. So there's a way to now rewrite this using Plucker relations until it is standard. So we have weakly increasing, strictly increasing down the columns. And then we can actually just look at both sides and immediately say whether they're equal or not. Okay, so I need to show you how to make this non-standard tableau, or sometimes it's called non-semi-standard, depending on the context. In rep theory, it's usually semi-standard. But I'll call it standard. And how do we do that? So we can check this by putting the left-hand side into standard form, and then we'll know if this is equal. So the 6, 4, I'm going to rearrange it. I'm going to keep the 1, 3 the same, and I'm going to swap the 6 with the 2, swap the 6 with the 3, and swap the 6 with the 4, giving me 3 terms. So you see the 1, 3, 1, 3, 1, 3, and then I have my 6, 2, my 6, 3, and my 6, 4 swapping. And this 1, 3, 3 is a determinant that has 2 columns the same, so it's automatically 0. So this term zeroes out immediately. And ignore this cross out. That's going to happen later. This is a standard. So this first term here, 1, 2, 5, 1, 3, 2, 6, 3, 4, I can rearrange with signs to make it in lex order. And it is standard. 1, 1, 3, 2, 2, 4, 3, 5, 6 are weakly increasing. So this is good. I'm going to put a box around it. It's one of the standard tableaux in my final answer. Okay. The other term, this third term here, the second term was 0. This third term becomes here, and uh-oh, there's a violation. 5 is greater than 4. So I need to straighten this out. And I'm going to do that by keeping the 1, 2 the same and swapping the 5 and the 1, the 5 and the 3, and the 5 and the 4, giving me 3 terms. The first one has a 1, 2, 1, so that's immediately 0. I can ignore it. The other 2 terms I will have to look at. I rearrange. One of them is standard, so I put a box around it. 1, 1, 2, 2, 3, 3, 4, 5, 6 is standard. That's this third term. But this second term here, when I rearrange, is going to be 1, 1, 2, 2, 4, 3. So 4, 3 is now a violation. So what am I going to do? I'm going to keep the 1 the same. I'm going to take the 4, 5, and I'm going to swap it in all the ways with the other columns. So 4, 5 swaps with 2, 3, giving me a single term. 4, 5 swaps with 2, 6, and 4, 5 swaps with 3, 6. There are my 3 terms. Okay. Now I will look at them and see which ones are standard. This one is standard. This one is not. This one is not. They both have violations. Okay, so the 6 and the 6 I'm gonna swap. So let's do this second one first. I've just, again, kept the 1, 2 the same. 1, 2, 1, 2, 1, 2. And then I swap the 6 with 3, 4, 5 in all ways. I look at the results, and they are all standard. So I put boxes on all of them. Now this last term is the last one I need to straighten. So there we go. I swap in all ways. And they are all standard. So now I look at all my boxed standard tableau. I see this one has a minus sign as this one, so these cancel. This one has a minus, and this is a plus, so those cancel. And the rest, 1, 2, 3, 4, 5, are all standard. So I have my 5 standard tableau, question mark equals a single standard tableau. Nope, they are not equal. So these two formulas do not agree. And we are already done. We can conclude that the graph is rigid. The only self-stress is the 0 self-stress, because this would have had to balance, and it did not. Okay, so this is the combinatorics of Young tableau. It's called Young's straightening law, and it tells you whether secret Pluker relations are going to cause flexibility in this graph or not. Summary: build source stream sinks. Follow weighted paths in the line graph. Pluker relations tell you if a self-stress will exist. That's basically it. Okay. So one last example. I'll take this. This is the octahedron, and we can follow the paths from source to sink. And here's one of them. Let's consider the source 4, 5. So where is it? 4, 5 is right here. So we can go to the sink in different ways. Here are two of the ways. Set them equal. And actually, both tableaux are already standard, so we don't have to do any sort of straightening at all. And they are clearly not equal. So we're already done. We've already verified that the octahedron is rigid generically. Okay. But I want to keep going because, yeah, we know it's rigid, but what if this were true? So let's remember what these columns mean. 0, 1, 2, 3 just means this determinant right here. It's a signed volume of a tetrahedron. And if we rearrange our equation here by clearing denominators, or no, not by clearing, just rearrange it like this so that vertex 0 appears here and vertex 5 appears here. And then we can apply a linear change of coordinates to R4. So remember, the relationships between these minors are completely invariant under invertible 4x4 matrices. And so flexibility and rigidity are completely invariant as well. And we call this sort of projectively invariant. That rigidity is a projective property. We can apply any sort of higher dimensional linear change of coordinates, and we have destroyed 0 information. So this will help us to understand this equation, this starred equation. I want to understand, what does it actually mean if this were true? This is not true generically. This equal sign is not true generically. That's what we discovered by looking at standard tableau. And that means that generically the octahedron does not have a self-stress. But by changing coordinates, we can look at what this means and say, look, if I look at the x's, which are now the barycentric coordinates of my 0th vertex in terms of the 1, 2, 3, 4 vertices. If I look at the x's, this ratio is going to be some number. And so that defines a quadric. This ratio is equal to some number k, and that defines a quadric. If then I place my 5th vertex with its barycentric coordinates y1, y2, y3, y4 in terms of this tetrahedron 1, 2, 3, 4, if I place it on that same quadric, then this equation becomes true. And even more, this quadric also has different lines on it, like the line through vertex 1 and 2 also satisfies the same equation. The line through vertex 2 and 3 does, 3 and 4, and 4 and 1 all do. So sort of 4 of the 6 lines all satisfy that quadric. And the octahedron becomes flexible exactly when we place vertex 5 on this same equation. And this is usually called Bricard's octahedron, and it's just kind of nice as a finishing example to show how it pops right out of our setup. So even once you determine that the graph is rigid, then there's some interesting things you can do to say, well, what are these equations mean geometrically in this case? It means that the 6 vertices of an octahedron lie on this quadric. And if they do, there is a self-stress and the octahedron becomes flexible. Okay, that's it. Thanks to Bernd, Martin, and Matthias for inviting me, and thanks to all of you for listening.